Welcome to the first lecture of module 2.
In the last two lectures, already we have discussed about a very basic modes of heat transfer, the conduction, convection and radiation, and then we discussed and derived the general heat conduction equation starting from a small differential element, and that we have derived for Cartesian coordinate, cylindrical coordinate as well as spherical coordinate system. Now, in this lecture I will try to be specific in the discussions, rather I would like to reduce the problem of general conduction into a simplified form. First of all, we will discuss in the Cartesian coordinate, and we will be discussing on one dimensional steady state conduction. So, we are going to discuss on one dimensional steady state conduction. We will start with the rectangular coordinate system. To start with, we will discuss a plane wall. Consider a plane wall and it is having, say, this is the direction of heat conduction, and at this point its temperature is say T1, and at this point its temperature is T2. Okay. Now, what we will do is, in this case we will see from both angles direct application of phenomenological law of Fourier equation, or rather Fourier first law, and that Fourier second law or Fourier field equation. We will see that how to apply this. Now, once we write for plane wall that rate of heat transfer q dot x, as because we have designated it to be in x direction. So, q dot x is equal to, we have already seen that minus k, k is the thermal conductivity, A is the area of heat transfer, and del T by del x. Now, what we will write, this del T by del x would be a perfect differential, because T is a function of x only, it is not function of other coordinates, also it is not function of time, because we have assumed that the discussion will be on steady state. So, therefore, we will write it as minus k A dt by dx, and at steady state the heat transfer rate should be constant. So, q dot x is a constant quantity, therefore, we can write that dt by dx equals to q dot x by k into A, so minus dt by dt is equal to constant, or what we can write is minus dt is equal to some constant equal to say C1. So, C1 into dx. Or what we can write as that, because dt by dx is a constant, we can write that dt by dx also we can write as say T2 minus T1 by, let the total distance is L by L. Under that situation, we can write that q dot x is equal to T1 minus T2 by L by k into A. So, we can say that rate of heat transfer is driving force by resistance. So, numerator is the driving force, denominator is the resistance. Now, this one can be, and this is the heat transfer rate, that is nothing but the heat flow, and that is equal to heat flow. So, we can explain this in terms of electrical analogy. According to the electrical analog, that current is the, say, differential potential is delta V by R is the resistance. Current is equal to potential difference by resistance, and if we just see from here, between two terminals, if V1 is the electrical potential at one point 1, and V2 is the electrical potential at point 2, and if R is the resistance, then we know that I is equal to V1 minus V2, which is the differential, by R, or that is equal to delta V by R. Exactly similar way, we can see that in this case, in place of being electrical potential, we will say it is the thermal potential, which is nothing but expressed in terms of temperature. So, at these 2 points, you have, say, at this point it is T1, and then you have a resistance, and then you have T2. So, we should say that this is the thermal potential T1 at this point 1, and this is the thermal potential T2 at this point, and what you get, the resistance you get at this point is R, and this is equal to L by K into A. K is the thermal conductivity. So, this way we can say that heat flow, which is the is equivalent to current flow, current or flow of charge, current or heat flow is equivalent to the driving force. There is electrical potential difference. Here is the thermal potential difference, which is nothing but the temperature difference by the resistance. Okay. Now, whatever we have seen here, if we try to see that, or if we try to apply the Fourier field equation, we have seen in case of Fourier field equation, the basic conduction equation, general conduction equation is that 1 by alpha del T by del T equals to grad square T plus Q dot Gen by K. So, this is the very generalized equation, and we have seen in the last class how to derive this equation. Now, for the present situation, which we are discussing now, a steady state, and if we say steady state, this is the one condition, no heat generation, this is the another condition, and one dimension only, say here one dimension means only in x direction, x directional heat transfer. So, under these three conditions, the above equations is gradually I am reducing the above equations to this form. So, first it will be grad square T will be equal to 0, that is the Laplace equation, and then you will be writing that del square T by del x square will be equal to 0, because the other two terms are also 0. It is only in x direction. So, what we finally can write that from this equation, we can write that d square T by dx square equals to 0, because T is a function of x only, T is a function of x only. Then what we can write is that T is equal to C1x plus C2, and these two constants C1 and C2 can be obtained by putting the boundary conditions, and we have to put two boundary conditions. So, boundary conditions are, you can say that at x equal to 0, T is equal to T1, and x is equal to capital L, T is equal to T2. That is what we have seen in the previous diagram. At x equal to 0, T is equal to T1, x is equal to 2, capital L, T is equal to T2. So, what we get from this, we can find out that T is equal to T1 minus T1 minus T2 by L into x. Okay. So, this says that it is the temperature profile along this. So, if we see the temperature profile, it is becoming a linear profile, and this profile is like this. So, this is T2. The profile is, it is a linear profile, sorry. So, it is a linear profile between point T1 and T2. Now, so this is the very simplest form of heat transfer on the steady state in one dimension. Normally, what happens that in case of in practical situations, there is a composite material is applied, particularly for insulating the furnace walls, as we have discussed. So, if we have say several such layers of materials that is being added for insulating purpose, so that heat loss is minimized, this kind of situation is basically used because to make the insulation material stable, and particularly happens in case of say, as I told you, in case of furnaces, or in a very common way that refrigeration systems in fridges, deep freezers or normal domestic fridge that we have seen, there are certain insulating materials are being put, and these materials have got different thermal conductivities, and because of the different thermal conductivities, they provide different type of resistances, and a person who is designing that particular instrument or that particular equipment, he has to be very careful to find out that heat loss amount, and to see that he has to find out the trade off between that heat loss and that cost of the insulation. So, he has to make a trade off that. So, if we see in case of composite wall, let us first consider a composite wall, draw a composite wall for these kind of situations. So, if I say that there are three composite walls of 3 layers, consider this, and here 3 different layers are there. So, this is the first layer, this is another layer, this is another layer. So, different materials are being applied for this composite wall. Say if we say that this is the direction x, and say this is the q dot x, that is being heat transfer is taking place from one side of the wall to the other side, and we will say that say this is A, this is B, and this is C, and say this distance, it is say LA, this is say LB, and this is say LC, okay, and so this is the heat transfer out. So, under this situation, what happens to the resistances then under steady state condition, and this is the one dimensional heat transfer along x direction, it is happening. So, what happens to the electrical analog to this? If we see that, in that case we can say that at this point, so if we say this is point 1, this is point 2, this is point 3, and this is point 4. So, if we draw, we will see that So, this is at point 1, this is say T1 is the temperature, point 2 T2 is the temperature, then T3 is the temperature, and here it is say T4 is the temperature, and you have different resistances between these temperature nodes. So, what is that these resistances are? We have seen the resistance is L by K into A. L is the thickness, and L K is the thermal conductivity, and already we have seen in the previously we have seen this resistance is equal to L by K into A. L is the thickness, okay, and K is the thermal conductivity, and A is the area of heat transfer. So, under this situation we can have like the resistances will be here, we can write that it is L A K A is the thermal conductivity into A is the area. So, if you see that area for all the cases are common. So, therefore, this, and here this say I will say that it is R 1 is equal to this, R 2 is equal to say L B by K B into A, and R 3 is equal to L C by K C into A, where K A, K B, K C are the thermal conductivities, A is the common for all the cases. Now, this way if we say, then we can find out at steady state, we can find out the like electrical analogues, we can find out that Q x dot is nothing but, so this is your R 1 is the resistance, this is R 2 is the resistance, this is R 3 is the resistance. We can find by like T 1 minus T 2 by R 1, this is the current through this from this point to this point, or the heat flow through this from this point to this point. And this at steady state there is no accumulation of energy. So, all the energy which is coming here, it will pass through, it will pass through. So, therefore, what is happening, this also will be equal to T 2 minus T 3 by say R 2, and this will be equal to T 3 minus T 4 by R 3. Okay. So, this is the driving force by the resistance is R 3. Also, it can be like this, this is also equal to say T 1 minus T 3 by summation of the two resistances R 1 plus R 2. This also can be equal to T 2 minus T 4 by R 2 plus R 3. This also can be equal to T 1 minus T 4 by R 1 plus R 2 plus R 3. So, under steady state situation, you can say that these are all with the help of these relationships, we can find out some of the unknown parameters may be there and some of may be known parameters, and we can find out these unknown parameters. For example, if we know what is my T 1, if we know what is my T 4, if I have to find out the temperature in these junction points, in these points, then we can find out from these several relationships we can use and find out what will be the values of the temperatures at the intermediate points. Also, we can find out then by measuring this, we can find out the temperature profile. Say for example, say this could be a temperature profile of this matter, depending upon the kind of resistance. If you see that here the temperature drops sharply, here the temperature drops is relatively less, and here the temperature drop is little more. So, what we understand is drop in temperature, it depends upon the resistance. Current flow is there. So, drop in temperature will drop in temperature from one place to the other place depends. So, when you have these, then you have very high resistance in these, and here the resistance is very less, and here is resistance is moderate. So, this way we can find out the temperature profile also at different points in case of a composite wall. So, if we see for a complicated case, for complicated composite walls, if you consider say suppose this, This is the composite complicated composite wall, where you can see. So, this would be like this. Here say this. So, this is say one type of insulation, this is another type of insulation, this may be another type of insulations, okay. And here you have a different type of insulation again. So, this is another type, and here you have a different type of insulations. The material which are placed maybe here, here are different, all the materials would be different. So, under that situation, what happens to the electrical aeronautic concept? So, what we will do is, we have to find out, if we have to find out the heat transfer rate from this side to this side, say q dot x, that is the heat, this is the x direction, we have to find out the total resistance of the system. Now, total resistance of the system, here we can say that in this, the three blocks, we can say they are in parallel. So, we will write like say this is again say 0.1, this is 2, this is 3, and this is 4. So, at 0.1 we have got like this. So, this is say T1 point, and you have all the three resistances, this one say R1, R2, and this R3, they are in parallel. So, you have R1, R2 and R3, and then you have again R4 and R5. Okay. So, again this R4 and R5, they are in parallel. Okay. So, this is T1, this is T2, then this portion is T3 say, and then between T3 and T4 there is one resistance like this. So, what we have to do is, so this is your R4, this is R5 and this is R6. What we have to do? We have to find out the resultant of these three in parallel, resultant of these two in parallel, and resultant of this is already there. So, summation of all these two resultants and these will give you the total value of the resistance. So, to calculate the total resistance R. Okay. So, RT we have to calculate like this. And we know, so for example, in this case what happens to the resultant of 4 and 5. So, R, say if I say that R resultant is equal to 1 by R resultant resistance is equal to 1 by R4 plus 1 by R5. So, from there you can find out, we can find out what is R, that is we can find out from this. This is equal to okay. So, 1 by RR is equal to R5 plus R4 by R4 R5, then R resultant R is equal to R4 R5 by R4 plus R5. This is the resultant resistance. Similarly, we can find out the resultant resistance for this case also. In this case also you can find out the resultant resistance in the similar manner. Now, after getting these all the resistances, then you add up and find out the. So, this is the resultant resistance 2. For this case you get a resultant resistance say RR1. So, RR1 plus RR2 plus R6. Okay. This gives you the R total resistance for this, and from there we can find out what will be the. So, Q dot X can be found out as say T1 is the temperature at section 1 minus T4 is the temperature at surface 4 divided by RT is the total. So, we can find out the heat flow rate for this kind. And now, we also know that what is R1. If we say R1 will be equal to, say if I say this is say A, V, C, it is D, it is E, say it is F, and we will say that it is a L A by K A into A by 3. Here the area is divided into 3, okay, because this part is equally divided into 3 parts. So, that area of heat transport is divided into 3 parts from this side. Okay. Similarly, R 2 is L B by K B into A by 3, and R 3 is equal to L C by K C into A by 3 in the case of first block. And if we see the second block, here it is divided into 2 equal parts. So, under that situation, say R 4 will be equal to say L D by K D into A by 2, and R 5 will be equal to L E by K E into A by 2, and we know what is R 6. R 6 is equal to L F by K F into A. So, this way we can find out the individual resistances, and from the individual resistances we can find out how to find out the resultant resistance for this case. For this case, is the parallel arrangements, and then we can find out what will be the total resistance for this, and then we can find out what will be the current through this. So, this way we can find out or analyze conduction problem, heat conduction problem through a plane wall, and you can see that we have only considered in this case the heat transfer through the walls, through the solid body by conduction. We have not considered anything about that convection that may be in place in the 2 sides of the walls or surfaces, that we have not taken into consideration as of now. We have assumed that the temperature at the surface and this temperature at the surface we have considered to be constant or at some values like T 1 and T 4. In this case, temperature of the surface is T 1, temperature of the surface is T 4, that we have considered as of now. But actual cases, in practical situations, there will be some temperature, there will be some fluid in this side, there would be some fluid in this side. So, what we have to see? We have to take into consideration the heat transfer, convective heat transfer also into account, that we will discuss in subsequent lectures. Okay. Now, whatever we have discussed, it is only one dimensional heat conduction at steady state without any convective heat transfer associated with these things we have considered. And also we have considered that there is no heat generation. Already we have seen in heat conduction, generalized heat conduction equation, there can be heat generation term associated with it. So, if you have a possibility of heat generation, say in a plane wall. So, if I draw again a plane wall, say this is the plane wall, and say total thickness is this, and this is say x. For simplicity or ease of understanding, so this is plus L and this is say minus L. So, the total thickness of the plane wall is 2 L, okay, and again under this situation, and we will assume that there will be a uniform heat generation in this plane wall. Under that situation, our differential equation or the governing equation, the general conduction governing equation, it is being reduced to Poisson's equation. I will show you how it is, that 1 by alpha del T by del T we have seen equals to alpha grad square T plus Q dot J by K. That we have seen already. This is the very basic conduction equation, and according to our analysis is the steady state. And but here I am trying to keep it here. I am trying to see that if there is an heat generation in this metal body, then what is going to happen? Under that situation, we will say that alpha grad square T is plus Q dot J by K equals to 0. but as we told that it is only in x direction. So, in that case what we can write is this alpha won't be there. Okay. So, we can this. So, we can write that del square t by del x square plus q dot gen by k equals to 0. Now, this equation if we solve, what we find is that t equals to del t by del x equals to minus q dot gen by k into x, okay, plus C1, and at say understanding the homogeneity, understanding the symmetric point of view of this. One is homogeneous, that we will assume it to be homogeneous, that it is uniformly heated, and if we consider the symmetric nature, because it is the center line, we can understand. So, at x equal to 0, we can say that dt by dx will be equal to 0, understanding the symmetric nature of the system, because it is the center line. So, actually I should write this one as dt by dx because it is only in x direction. So, we can write now that dt by dx is equal to, and under that minus q dot gen by k into x. If you further integrate this, then we can get t is equal to minus q dot gen into x square by 2k, this is 2 plus C2, and again here we have to put some another condition, another boundary condition, and the boundary condition is that at x equal to L, T equals to say Tw. So, that is the wall temperature. So, under that situation what we get is that Tw is equal to minus q dot generated into x square by twice k, here x will be equal to replaced by L square plus C2. So, from there we can find out that T minus Tw is equal to q dot generated by k into L square by 2 into 1 minus x by L whole square. So, this is becoming the temperature profile in that plane 1. So, that means if there is a heat generation involved q dot gen, then it is not remaining as a linear profile as we have shown previously. It is going to be a non-linear profile with a maxima at the center point, that what we have seen. So, we have told that this is say Tw, this is again Tw, and there is a maxima, and here it is say T max. Okay. And the values of, these are the wall temperatures at x with this, and values of T max, we can say that values of T max is we can find out by putting x equal to 0. At x equal to 0, that is equal to T max. So, you can say that T max is equal to Tw plus q dot gen by k into L square by 2. So, this happens to be the maximum temperature in this case. Now, it may happen in the other way around, that in place of having a heat generation, it can be that heat depletion, that means heat is coming down. That means heat removal has taken place. Under that situation, if there is a heat removal, so in that case it will be just opposite to this. So, it will pass through a minima. So, in place of having a T max, here it will be T minima, and that value also be obtained from this. Here the sign of this will be reversed from the value. If the value, putting the value, if when there is a heat generation, this will be positive, when the heat depletion, heat removal, this value will be negative. So, in that case it will be automatically, this T max will be this. So, we can say in a much effective way that T max is equal to T w plus a mod of q dot gen by k into L square by 2, whereas T minimum will be T w minus mod of q dot gen by k into L square by 2. So, that gives a fair idea about how the profile will be. Now, there can be a situation when one surface of this, whatever we have discussed, so one surface of this is insulated. There can be a situation when one of the surface is insulated. Under that situation, what happens to the temperature profile? If we see, say, if we do it again, say this is the plane wall and this is the center line. Now, what I will do is I will write at x equal to 0 here and x equal to L here, and if we assume that this is, say, this surface is insulated. If this surface is insulated, under that situations our boundary conditions have changed. So, what will again this boundary condition remain the similar, only thing is that the location has changed. So, we have in the previous case also we have written at x equal to 0, we have written that dt by we have written that dt by dx is equal to 0. This indicates that maxima or minima condition. Here also we are doing the x is equal to 0, dt by dx equal to 0, but only thing is that in comparison to the previous case it was like this and this was the center line, x was 0 here, okay, and the profile was like this. In this case the x is 0 here, and then what we have written is L and x is equal to L, you have T is equal to T w. Same thing is possible here, it is T w here, it is T w here. Okay. So, then what is happening is, if we try to draw that, this profile will be now like this. So, if you see that this becomes the same profile is this. So, under that situation this total thing represent these total things. Okay. So, that way when one surface is insulated, the profile is shifted like this, it becomes like this. So, this becomes the profile for insulated, one surface being insulated for a plane wall. Okay. And then the equation remains the same, that T minus T w by T naught minus T w is equal to 1 minus x by L whole square, where T naught is equal to T at x is equal to 0, as what we have seen. So, we can say that this value we have obtained from this from the equation T minus T w is equal to q dot gen by k into L square by 2 1 minus x by L whole square. Here if we put at x equal to 0, t equal to t 0, what we have put as the t max or t min, we will write t 0 minus t w is equal to q dot gen by k into L square by 2, that is all. So, we can write now temperature profile T minus T w by T 0 minus T w is equal to 1 minus x by L whole square. So, that is what becomes the, that is what remains the temperature profile at this present case also. Fine. So, now we have tried to give you some idea about that heat conduction heat conduction through the plane wall. We had tried to give you some idea on this. When there is steady state, heat conduction only takes place in one direction, and there is heat generation, or there is no heat generation. Under both the situations, we have seen how it happens. Now, we will say we will take up a few problems to discuss on this particular matter. So, suppose the first question, if I say question 1, what happens to the temperature distribution when we have seen what happens to the temperature distribution in a plane wall when thermal conductivity K is written as K naught into 1 plus C into T. C is a constant. So, this is the question. What happens to the temperature distribution in a plane wall when K is written as K naught into 1 plus C into, I am sorry, this I will write, this is not time, this is temperature. We have seen that in case of plane wall, when thermal conductivity K is constant, we have seen that temperature profile is a linear profile between points T1 and T2. That is what we have already seen. This is the simple. Now, if K is constant means, that means if K equals to constant means implies C equals to 0. When C equals to 0, K equal to K0. So, this is the case. When C is not equal to 0, so K has a link with, K has a relationship with temperature. The temperature changes in this plane wall. So, what happens to that? So, it is a very simple one. So, what we have to do is, we know that Q dot X, already we have seen using that phenomenological law, Fourier first law, you can say Q dot X is equal to minus K into A into dt by dx, because one dimensional heat transfer we are considering. So, this is that Q dot X is the x direction. Okay. So, here K will be replaced by K naught into 1 plus Ct. That means minus K naught 1 plus C into T into area into dt by dx, and we say that it is a steady state. This is the, understand, it is a, whatever we are trying to discuss at this point in this lecture, everything is in the steady state condition and one dimensional heat transfer. These are the two major things. So, these are the two important things are always there in the behind all the discussions. So, one dimensional heat transfer and steady state situation. So, when there is a steady state, so Q dot X, the heat flow rate will remain more or less the constant. So, based on that, what we can write now? Now, we can do the integration. If we do the integration, what we will get is that dt or say dx is equal to say Q dot x dx is equal by Q dot by A, okay, and also you can write that K naught, Q dot by K naught A into dx will be equal to integral of that will be equal to integral of 1 plus Ct into dt. So, if we just do the integration for the points say x equal to 0 to capital L, if I say this is 0, this is capital L, and here it is T1, this is T2, okay. Then what are you getting is if you do the integration, then it will become like this. Q dot x by k naught into A into L, okay, will be equal to your T plus C by 2 into T square, and that will be equal to, there is a negative term here. So, that this would be changed to this, and so from there we can write that Q dot x is equal to T 1 minus T 2, this part will be like this, 1 plus C by 2 into T 1 plus T 2 by L divided by K naught area. This is the resistance. This is the resistance, this is the driving force, and this is the extra term. When C comes to 0, it is a simple T 1 minus T 2 by this, what we have already seen. But when C is not 0, then you have an extra terminology. That means the profile becomes a nonlinear in nature, and the nonlinearity is like this. When if C is greater than 0, you will be getting this equation. When C is greater than 0, this profile, and this kind of profile you will be getting when C is less than 0. I am sorry. This kind of profile will be there when C is less than 0, and if we see in a much better way, this kind of profile will be there when C is greater than 0. So, this equation establishes that relationship. Depending upon the values of C's, you will be getting the profiles here. Okay. Now, I will come to another problem, say problem 2. The problem 2 says that the area of the door of a domestic refrigerator, the area of the door of a domestic refrigerator is 0.5 meter square. The door is a composite of insulation, which is 20 millimeter thick, and K is equal to 0.25 watt per meter per Kelvin, and metal sheet. We know that there is a metal sheet in the outer side of the refrigerator, and inner side is that insulation part, which is of 20 millimeter thick, that means 2 centimeter thick, and the metal sheet, which is say 2 millimeter thick, and K is 40 watt per meter per Kelvin. Now, what is the total resistance of the composite wall? What is the total resistance of the composite wall? And if the insulation surface temperature inside the free refrigerator is 0 degree centigrade, and the surface temperature of the metal sheet in contact with environment is 30 degree centigrade, then what is the heat loss? What is the heat loss? So, basically what I am trying to say that, say suppose this is the insulation and you have a metal sheet, and this is the, you can say that this is the door, okay. This is the door and this is the insulation, and this is the metal sheet. Now, what happens to the, so heat will be in leak from this side to this side. This is the environment and this is the refrigerator inside. So, here this surface temperature is 30 degree centigrade, which is in environment, and this surface temperature is given as 0 degree centigrade. So, what is there is, there are two resistances. We have seen that according to the problem there are two resistances and this another resistance this. So, this first resistance is due to the insulation and this resistance is due to the metal sheet, and here the temperature is 0 degree centigrade and here the temperature is 30 degree centigrade. So, if you say that this is resistance R1 and this is resistance R2, R1 we know that it is say L1 by K1 into area, and that is equal to, we can calculate, L1 is 20 millimeter thick, 0.02 meter, and by K1 will be equal to 0.25 into 1, and R2 will be equal to, and that is 2 millimeter thick, that is 0.002 meter divided by, and K2 is equal to 40 into area is equal to again 0.5. So, it will be 0.5, this much. So, we can find out from this what will be the area, that we can find out that is equal to say 0.04 Kelvin per watt, and R2 will be equal to say 0.000025 per watt. So, that your current Q dot X will be equal to total temperature difference is 30 divided by R1 plus R2. So, by this we can find out this in terms of watt. We can get the value of what is the heat loss by these calculations. Okay. And one thing I have tried to say here is that you have to check these calculations, maybe this will be 16 0. I am sorry, this will be 0.16 and here it will be 0.0001. So, anyway, whatever may be the case, so you have R1 plus R2, this will be added here and you will get this current. Now, what happens here, it can be seen that the value of resistance for the metal sheet, and if you compare these two, they say almost 1, 2, 3, 4, 10 to the power 3 times, 10 to the power 3 times difference in the resistances is there, and that creates a problem. Therefore, we need to have insulation. You cannot put, and this 10 to the power 3 times is reflected, you can see from the thermal conductivity values, it is something like that 10 to the power 3 times, and therefore, this high difference in the thermal conductivity values create a high difference in the resistances, and therefore, normal metal sheets are not useful. You have to put when normal metal sheet has very poor resistance. So, heat can easily be leaked or transferred into the system. So, what is to be done? Insulation has to be put if you have to prevent any heat transfer, heat loss. Thank you.